Kids, look what I saw when I drove to the bank today, right? Just driving by, seeing if my bank was open, and look at what it was saying. Unit 5. It's time to start Unit 5. Graphs and inverse graphs of trigonometric functions. Woohoo! Unit 5. Let's go. All right. So we're going to start with graphing. Graphs of sine and cosine, right? Sine and cosine are the two trigonometric functions that everybody else is built off of. So, of course, knowing your unit circle really, really well, and because that's where sine and cosine were developed, right? Our unit circle, where every radius is of unit 1 and has the coordinate x comma y, which is also the cosine and sine. Right? So the x coordinates around the unit circle are all cosine values, and the y coordinates all the way around the circle are your sine values. And then we have quadrants, right? Quadrant 1, where sine and cosine are both positive. Quadrant 2, where only sine is positive. Quadrant 3, where only tangent is positive. And quadrant 4, where only cosine is positive. Of course, quadrant 1, where everybody is positive, right? So this, we're starting with AF material, right? You did this last year where you're going to be asked to identify and know the vocabulary, amplitude, period, vertical shift, phase shift of any sine or cosine graph. And you'll be asked to sketch sine and cosine graphs with transformations. And you're going to be expected to graph and label them the way we model in these videos, right? So when you do an assessment in this unit and you get something back and you've got labels, but I say it wasn't labeled correctly, I'm always going to refer you back to how we do it here and on our homework assignments and practice assignments. So here is a nice applet that shows you unwrapping the unit circle. So taking all those coordinates, the cosine and sine coordinates off of the unit circle and spreading them out onto an axis. So y equals sine of x is over there to the right of the unit circle, right? As you travel quadrant 1, quadrant 2, quadrant 3, quadrant 4. And cosine of x, or cosine of theta, is going down vertically through there, right? Kind of cool, right? Taking all the x coordinates off of the unit circle and associating with every angle what's the x coordinate, with every angle what's the y coordinate. Those are your graphs of sine and cosine. So here is a graph of sine, right? Our default is radians. So, and especially usually when we see the variable x instead of theta, we think radians. So you can see that for sine x, it's got an infinite domain. We usually focus on one cycle that starts at 0, and sine x through quadrant 1 is positive and rises to a value of 1 at pi over 2. Then through quadrant 2, sine is still negative, but is decreasing until pi, where sine is 0. And then in quadrant 3, sine is negative, getting more and more negative until 3 pi over 2, where sine is equal to -1. And then in quadrant 4, sine is still negative, but increasing till 0. So one rotation around the unit circle in a horizontal distance of 2 pi radians. That's the circumference, one trip around the unit circle. But of course, I can keep spinning and spinning, which is why the sine curve goes on and on forever. And you could just copy and paste that blue piece. Notice that in quadrants 1 and 2, the graph of sine is concave down, and through quadrants 3 and 4, the graph is concave up with a point of inflection at pi. Notice that sine is increasing in quadrant 1 and increasing in quadrant 4, but decreasing in quadrants 2 through 3, 2 and 3. Cosine is just a shift of sine, right? It is just the y-coordinates. You're just looking at the same angles, the same arcs, but you're looking at the x-coordinates instead of the y-coordinates, but it is the same freaking circle. But cosine of, so we also orient ourselves starting where x is equal to 0. Cosine is 1, right, out there at the far end of on the positive x-axis. And then cosine through quadrant 1 is positive, but decreases until 0 at pi over 2. Then in quadrant 2, cosine is negative and gets more and more negative until cosine is negative 1 at pi. Then in quadrant 3, cosine is still negative, but coming back towards 0, where cosine is 0 at 3 pi over 2. And then in quadrant 4, cosine is positive and increases again till 1. Notice that cosine starts off concave down, has a poi at pi over 2, and then is concave up through quadrants 2 and 3, has another poi at 3 pi over 2, and cosine finishes concave down again. Notice that cosine, if you start normal cosine, this is our parent graph. Normal cosine starts at a maximum and hits the sinusoidal axis twice in a distance of 2 pi radians, which is 1 trip around the unit circle. The middle, right, we call where you bounce back and forth, right, with a radius of 1 and negative 1, right? The sinusoidal axis is y equals 0. But for sine, we have the same sinusoidal axis, the same middle, but notice sine starts on the sinusoidal axis, is where it starts, and it ends on the sinusoidal axis, and it hits the sinusoidal axis a total of 3 times in one cycle. Sine has 1 max and 1 min in that one cycle, whereas cosine has 2 max and 1 min. In our normal cycle of completing a cycle within a distance of 2 pi. Okay, so that's some AAF review of our sine and cosine graphs. So here's the general form of a sinusoid. And a sinusoid, even though it has sine in it, a sinusoid is either sine or cosine, because they are just horizontal shifts of one another. Now in AAF, we had a slightly different form of this equation. We said this was capital A sine B x minus C plus D, okay? This book just calls it differently. Different websites use different things, but as long as you understand what each place represents, a multiplier on sine, a multiplier inside of sine, a shift inside of sine, a shift outside of sine. In AAF again, that's how it looked in your AAF notes. A is the dilation factor. The absolute value of A is the amplitude. Amplitude, think distance. So distance is always positive. Distance from the sinusoidal axis to a max or a min, right? A dilation factor, if positive or if negative, you have an idea of what happens, right? But remember, if your sine and the dilation factor is positive, you will start on the sine. When we orient ourselves at 0, you'll start on the sinusoidal axis and increase. But if your sine and the dilation factor is negative, you will start on the sinusoidal axis and decrease. Cosine, if the dilation factor is positive and your cosine, you will start at a max. But if you are cosine and your dilation factor is negative, you will start at a min. So hopefully, here's a graph. It was the exact same graph I used in AAF, actually, where you can see, well, let me erase that other stuff. Right? You can see y equals a sine x, and all I've done is change the dilation factor. The purple has a dilation factor of 1. That's our normal sine curve. So hopefully you can, starting at 0 and ending in pi, 2.6-ish. I'm sorry, 6.28-ish. One cycle is finished in a distance of 2 pi. But when you change the dilation factor to 2, you can still see that you start at 0 and increase. You still hit the sinusoidal axis in the middle, and you end on the sinusoidal axis, but your distance to the max and mins from the sinusoidal axis is now 2, distance of 2. And then hopefully you can see the same thing with the one that has a distance of 3, the distance of only a half, and a distance only of 1/5 or 2/10. The period is a length to complete one cycle. So remember, amplitude is a distance from the sinusoidal axis to max and min. Period is the length it takes to complete one cycle. Normal amplitude is 1. Normal length, normal period is 2 pi when you're in radians, and 360 when you're in degrees. B is found from the equation. B represents also a length. Well, no, I'm sorry, not a length. B is a number of cycles completed in your normal period. 2 pi radians or 360 degrees. So B is actually just a number. How many cycles am I, if I look at a distance of 6.28 radians, how many sine cycles am I going to see complete within that distance? But when I'm graphing, I really want to know, how long does it take to complete one cycle? That's the period. So the period, you have to take our normal, right, circumference and divide by B. Normal period is 2 pi, a 1 trip around the unit circle, the radius of 1. H is called the phase shift, right? That is a translation, right or left. And y equals k is the sinusoidal axis, right? That's the equation, is the equation of the sinusoidal axis. K itself is how far you went, shifted the whole graph up or down. So these are just new names for old things. Dilation factor is an old name. In trig, we call that the amplitude, right? Phase shift is a new name. We call phase shift, that's a trig word, but in normal land, we call that a horizontal translation, right? Y equals k is the equation of the sinusoidal axis. In normal land, we call that a vertical translation, right? So the dilation factor is a vertical stretch or shrink. The period is a horizontal stretch or shrink. The phase shift is a horizontal translation, and k is the vertical translation. So I could give you some equations and just ask you to describe, use this vocabulary, and talk to me about transformations. IB in particular is very keen on you writing out translations. So let's take a look at this Desmos, little Desmos applet first, where we can mess around with those things. So I have the graph of sine on right now, where sine is, and I've shifted A, I've changed A to a negative dilation factor. So if you look at 0, sine with a negative dilation factor starts decreasing. Notice the middle, the sinusoidal axis is still at 0, right? You see k is still at 0. If I move k though, right, the whole graph just shifts up and down, up and down. If I change h, moves the graph right and left, right? Notice that when h is positive, x minus h, I move to the right. When h is negative, I would have x minus -2 or +2. Notice my starting point is here at -2, and I decrease from, because my dilation factor was negative. Let's put this back at 0. 0. Now let's change b. Remember, b is how many cycles you see in a distance of 2 pi. So I'm going to change the amplitude, gosh darn it, back to 1. Notice starting at 0, right, 1.5-ish, which is pi over 2, 3.14-ish, which is pi, 3 pi, 3/2 pi here, and 2 pi, 6.28. Look at that distance right there. Do you see it? That is a distance, and one cycle is completed in a distance of 2 pi. B is equal to 1. Look what happens when I make b equal to 2. Look at that same distance. Here's 2 pi. How many cycles do you see? Starting at 0. From 0 to 2 pi, how many cycles do you see? Right, 2. If I make this 3, look at that same distance. 2 pi. How many cycles? What if I make b a half? No, not negative. We're not going to ever deal with it being negative. A half. Look at that distance. There's 2 pi. How many cycles do you see? Half a cycle. Right? Kind of cool. And then I can do the same thing with cosine. The amplitude is 1. I start at a max. Right? But at a distance, since b is a half, at a distance of 2 pi, I only see half of the cosine circle. So let me make b 1. Right? There's normal cosine. Start at a max, hit the sinusoidal axis once, go to your min, hit the sinusoidal axis again, return to the max at 6.28-ish. One cycle. If I make a -1, I don't start at a max, I start at a min. If I make stretch a further, right, my amplitude, the distance from the sinusoidal axis, gets larger and larger. Here's me moving right and left. No shape change, just translate right and left. And here's moving up and down. Right? Do you see this? Not only, right, everything moves. The sinusoidal axis moves. The sinusoidal axis is at y equals 0. Right? Sinusoidal axis, the middle of the road, changes as I change k. Again, notice what happens when I change b. Change b to 3. Look at 6.28-ish. How many cosine cycles? 1, 2, and 3 in a distance of 2 pi. Right, so you can play around with this if you like. Just kind of cool. This link is here on the PowerPoint. So maybe you want to pause the video here and see if you can determine the amplitude, period, phase shift, sinusoidal axis, and then also describe the transformations of these three. Or you can go along with me. So amplitude, they ask for the amplitude. That's the absolute value of the dilation factor, which is 1/2. The period, right? Normal period is 2 pi divided by the value of b, but the value of b in this case is just 1. The phase shift is +3, right? It's x minus the phase shift. The sinusoidal axis is not 1. Sinusoidal axis has an equation, y equals 1. So amplitude, period, phase shift, sinusoidal axis, describe the transformation. You talk about amplitude as a distance from the sinusoidal axis to the max and mins. You say the period, it takes a distance of 2 pi. Two pi units. The normal cycle, which starts as 0, starts at 3. And the sinusoidal axis and the whole graph has been shifted up 1 unit. You could also talk about here, instead of cycle starts 3 units to the right, you could just say graph has been shifted 3 units to the right. That's fine. Don't get trapped. The amplitude is the absolute value of the dilation factor, so that is 4. The period is 1 trip around the unit circle, divided by the value of b. My phase shift is 4. Oh, I've just made a mistake. It's -4. No, I've still made a mistake. Do you know what it is? By the way, the sinusoidal axis is still y equals 0, right? Because it's +0. Look at that phase shift. Do you see the issue? You need to factor out 1/2. So you need to rewrite this equation. This equation is actually -4 cosine, factor out b so you can see the phase shift. Divide 1/2 by 1/2 and you get 1. Divide 4 by 1/2 and you don't get 2. 4 divided by 1/2 is 8, right? 4 divided by a half is 4 times 2, which is 8. So my phase shift is actually what? Is it 8? Nah, is -8. Now describe the transformations, right? The distance to the max or min from the sinusoidal axis is 4 units instead of 1. 1 cycle is completed in a distance of what? 2 pi divided by 1/2 is a distance of 4 pi, right? Graph has been shifted 8 units which way? And sinusoidal axis didn't get shifted at all, so I don't have to talk about transforming it. Shifted. Okay, be careful. You have to match the form. That's why in your notes you should have the form. The form is B parentheses X alpha theta, whatever you want, minus H, your phase shift. So let's look at the last one. Amplitude is 3/2. Your period is normal trip around the unit circle divided by B. My parentheses is closed here. So my phase shift is 0, but my sinusoidal axis is y, or g of t, equals -4, I guess up here. I should have put f of alpha. Describe in words, right? Distance to max min from sinusoidal axis. One cycle is completed in a distance of 2 pi over 3. There is no phase shift, so I don't have to describe it. And the sinusoidal axis and the whole graph have been shifted down 4 units. I have just painstakingly written out what I want you to write to me when I give you an assessment and ask you to describe the transformation. Please model my words. All right, let's go on. Construct, which means write, a sinusoid, which means choose sine or cosine, with the amplitude and period that they've created or they've given us, and they've given me a point that I must pass through. So I'm going to start at 0, 0. Now there's a lot of correct answers here. There's a lot of sine and cosine equations that can satisfy these conditions. Since I must start at 0, 0, I could make 0, 0 a max. I could choose to make 0, 0 a min. Why don't I choose it to be the sinusoidal axis? No, I don't have to write +0. I need an amplitude of 2 So I'm not going to go above 2, and I'm not going to go below -2. And a period of 3 pi means I'm going to stop at 3 pi if I choose to start at 0. Now, remember, I need to, right, draw a graph here. If I'm going to start and stop on the sinusoidal axis, I can either go up from the sinusoidal axis or down. If I go up, oh, it's terrible. It wasn't very symmetric there, was I? I have a sine with a positive dilation factor. So I make I leave the amplitude at 2. Then I have to have B. I have no phase shift. And now, since I have my period, right, is 3 pi, how do I find B? I need to know how many cycles are completed in a distance of 2 pi. Well, it's some portion of 3 pi, right? So my period is 3 pi over B. I'm sorry, period is 2 pi. My period is 3 pi, but the formula for my period is 2 pi over B, but I know my period is 3 pi. Solve that for B, and you get 2/3. Right? B times 3 pi is equal to 2 pi, and you're going to divide everybody by 3 pi, and the pi's will cancel out. Right? But again, there's lots of I could have made a cosine, I could have made sine with a negative dilation factor, right? There's lots of things that I could have done. I think this was probably the simplest one to do, and no, you don't have to write the +0. So we gave you these notes in AAF, what we call the roadmap to success. When you're asked to graph sine or cosine, start with your sinusoidal axis. Where's the middle of your road? Right? It's a dashed line because it's not part of the equation, not part of the right solution set. How wide is the road comes from your amplitude, right? So I draw a top of my road and a bottom of my road. And my sinusoidal axis is in the middle of my road. Where's the beginning of your road? I look at the phase shift for the beginning of my road. Say, how far from 0 do I go, right or left, to start? Where is the end of the road? I take my period, right? How long does it take to complete one cycle? Which is 2 pi over B, but I add where I start, right? So this is where you had your start plus the period, right? So that's equals the end of my road. Then you need to know where are what I call the road marks, right? If you think about like mile markers on the highway, you have to label basically the quadrants, right? Where you start, where you started, then take your period and divide it by 4 for 4 quadrants. And you're going to label where quadrant 1, right? You're going to be label the beginning, then the end of quadrant 1, the end of quadrant 2, the end of quadrant 3, and the end of quadrant 4. I call these the quarters. Don't forget back at the beginning too, once you're ready to draw, you go back up here to how wide is the road and you think about the dilation factor. Being positive or negative, and whether you are graphing sine or cosine. So let's do 2 examples together, and then I'll practice more when we are in our live session. Okay, without a calculator, here's the graph I want you to come up with. -3 is the dilation factor, so my amplitude is 3. My period is 1 trip around the unit circle, 2 pi, divided by how many cycles are in a distance of 2 pi. I have no phase shift, and I have no vertical shift. But I am graphing sine with a negative. So my sinusoidal axis, I start with the middle of the road. I do from a distance from the sinusoidal axis to maxes and mins are a distance of 3. And I draw the bottom of my road. It's terrible. And the top of my road. I mark where I have no phase shift, so I'm starting at 0. And sine starts on the sinusoidal axis. My start is at 0. Add my period to it. So the end is going to be at pi on the sinusoidal axis. Then I'm going to do my quarters, my road marks. My quarters are the period divided by 4. So I am going to add 1/4 of pi, add another 1/4 of pi, add another 1/4 of pi. So this is 1/4 pi, comma, sinusoidal axis, 2/4 pi. Of course, I would write that as pi over 2, comma, sinusoidal axis, 3/4 pi, comma, sinusoidal axis, and then 4/4 pi, which of course is 1 pi. So that's a check that I've done this right. Now I look at my dilation factor. A is negative. So I'm going to start on the sinusoidal axis, but decrease to the mixed minimum, increase to the sinusoidal axis, keep increasing to a maximum, decrease to the sinusoidal axis. And then, of course, indicate that I know that this pattern goes on. And this is how we expect you to graph without a calculator. Graph and label over one cycle, right? One cycle, one period. Label any sinusoidal hits. Label maxes and mins. Pi over 4, bottom of the road. 3 pi over 4, top of the road. Awesome smossum. I should erase the top of my road and the bottom of my road. I don't care if you do, though, and neither will IB. AP doesn't need you, AP needs you to know your sinusoidal graphs very, very well. Rarely ask you to sketch them, right? Or that you or grade you on sketching them. You need to know what they look like in order to do calculus, but IB is does make you graph, does make you label, does make you describe transformations in words. Let's do one more. G of t is equal to 300. What the heck? All right. It's okay. I can deal, right? My amplitude is 300. I am graphing a cosine graph with a positive dilation factor. My b, this really looks like pi over 2t, right, is what that really looks like. Therefore, my b value is pi over 2, so my period is 1 trip around the unit circle divided by how many cycles you see in a distance of 2 pi, and that, of course, is equal to 4. I don't have a phase shift, so I'm going to start at 0. I'm going to add my period to get the end, which is 4. My quarters are the period divided by 4. So, and my sinusoidal axis is still normal. I am going to go up from the sinusoidal axis a distance of 300 and down a distance of 300. I want to start right oriented from 0 and go a distance of 4. And my quarters are 1, 2, 3, and 4. Top of my road, bottom of my road. This time I am drawing a cosine graph, so I don't start on the sinusoidal axis with a positive dilation factor. I start at a max. I go down and hit the sinusoidal axis, continue down to the minimum, come back to the sinusoidal axis, and end at a max. Make sure your arrows don't go above or below your road. Label your maxes. Label your sinusoidal hits. Label your mins. Done and done. Okay, these would all be on non-calculator portions. These are the labels that I want, the shapes that we want, and equation of your sinusoidal axis labeled. If you called it y, I would not take off points, right? Maybe a half point, no, right? It's important that you label it as an equation. All right, so we'll do more practice of this in our live session. We'll see you then.